Hey everybody, today we're getting started on volume from the calculus perspective. So we have a few volume formulas, things like pyramids and cones and so on, but there are many shapes in the universe whose volume we might want to know. I drew one. Suppose we want to find the volume of some irregular shape like this. The big idea in calculus is to slice your shape up into smaller pieces, approximate the volume or area or whatever, and then use the definite integral to add up all of those smaller pieces to get the whole. That's what we're going to do here. So let's draw an x-axis underneath our shape. This is going to let us keep track of where our slabs are. Then let's start slicing it. We'll take very thin slices. The width is going to be, the thickness of that slab is going to be dx, a very small change in x. If we take that slab and pull it out and lay it in front of us, we can calculate its volume, dV, a very small amount of volume, as the product of its cross-sectional area, A, times its thickness, dx. So then the way we're going to get the volume of the whole shape is by integrating that dV along the entire interval where slabs actually exist. So if the shape begins at x equals A and ends at x equals B, the total volume is going to be the integral from A to B dV. The integral from A to B, A of x dx. This is an incredibly powerful formula that we can put to work right away. Let's start with a simple example verifying a formula that we already know. Let's look at a cylinder of height h and radius r. Let's lay it down on the x-axis so that x is measuring how far we are away from one of the bases. X is going to range from 0 to h here. So let's start slicing it. At every x value, we get this disk like I've drawn on the right. The radius is r and the thickness is dx. The volume of that disk is going to be pi r squared dx. The area of that circle, pi r squared, times the thickness. All the slices are the same here. Now to get the total volume of the cylinder, we integrate that from x equals 0 to x equals h, where the disks start to where the disks end. We integrate that volume element, dV, pi r squared dx. Remembering that r is a constant here. It's just a fixed radius of this cylinder. X is the variable. Overall, we get the familiar formula that the volume of a cylinder is pi r squared times the height, pi r squared h. Let's do a harder example. The base of a solid is a semicircle of radius 6 sitting on the x-axis. Cross sections parallel to the y-axis are squares. What's the volume of the solid? Okay, this is a hard shape to even envision. My best advice is to start by drawing the base. So in this case, a semicircle of radius 6. That at least we can picture and draw fairly easily. And then trying to draw in some cross sections as best you can using a little bit of perspective drawing, hopefully. So here's my rough thumbnail sketch. You can see that semicircle sitting on the x-axis. The radius there is supposed to be 6, so it runs from -6 to +6. And then I've drawn a few cross-section, all squares. It's also a good idea to draw one of the typical slabs like I've done there on the right. So the length of one of the sides of that square is going to be y, the height of the semicircle at any given x value. And the thickness of the slab, as usual, is going to be dx. Warning, this is an unfamiliar shape. It's very unlikely that any of us have seen this shape actually in the real world. It's not going to be any cross-section or fraction of a sphere. If you're hovering up above this thing, looking down on it, you will see a semicircle. But if you're standing far away on the x-axis and looking down at it laterally, the cross-section you're going to see is going to look more like a square. And there's no way you can slice a sphere to get a cross-section that is a square. So this really is an unusual shape. The good news, as unintuitive as this shape might be, the volume isn't going to be too bad to calculate. Once we have this slab drawn, we can write a fairly simple formula for the volume of that slab. dV equals y squared dx. So overall, this is going to be the form of our integral that's going to give us the volume. Integral from A to B, y squared dx. Two problems, two things we've got to deal with before we can actually do this integral. First of all, we can only have one variable when we do a definite integral. So we've got to get that y squared out and get some x's in its place. Second of all, the limits of integration, a and b, are just placeholders, so we need to get some actual numbers in there. So we're going to get the y squared out by using the formula, using the equation of that semicircle. So it's radius 6, so x squared plus y squared equals 36. If we solve that for y and just keep the positive part, we get square root of 36 minus x squared. That's going to be what we plug in for y. Secondly, the limits of integration, we know, are going to be from negative 6 to 6. It's a semicircle of radius 6. So just from the geometry, we know what the limits of integration are going to be. Overall, the volume is going to be the integral from negative 6 to 6 y squared dy, written with the y squared taken out, and the square root of 36 minus x squared put in for y. We get this. The square and the square root cancel, so we get a fairly simple integral at the very end. The actual computation in this problem is going to be the easiest part. So let's do it. We anti-differentiate. The x squared becomes a 1/3 x cubed, and we need to plug in the limits of integration. Here's what we get. Simplifying a tiny bit, the answer is 288.